Hey folks, Mrs. White here. Hoping you all are happy and healthy at your houses right now. I certainly am at my house a lot, getting a little stir crazy, but still here for you folks and prepping new materials. Um, Today is kind of exciting. We're going to start our last chapter for this year. We actually aren't super duper far behind from where we should be. Usually, we're about halfway through this unit at this point in the year, and then we have the last few weeks for chapter 7. So there's really only one chapter and only the first two sections of that chapter that you folks are going to miss out on. So it's not a huge deal. But it's very, very exciting that today we're starting chapter 6, and that's going to be the new learning for the rest of the year. If you haven't already, I would encourage you, and I think I already have in the past, to go to our classroom, go under the classwork tab, and then down here you'll see a link to a calendar of what we're going to be doing kind of every day and when the office hours are going to be held. So you folks finished your tests. Here's today, 6-1. We're going to be looking at graphing exponential functions and what is an exponential function. Okay, so hopefully you all have had your tests in, and I will be correcting those as soon as I can. Okay, I have over 40 honor students, and so I want to be able to leave you notes on how you did and what mistakes you made before I release your grades back to you, so annotating those takes a little bit of time since I'm not holding them in my hand. Anyways, I will get those turned in as soon as possible. Chapter 5 was not your last test. If you come down here, the last week of school, so the 5th is technically your last student day, I will be giving you a test. Okay, really, it's from any time after this review. I would even do it Monday afternoon if you were interested, all the way through until the 4th. That way I'm able to correct it and get my grades in on the 5th. And so chapter 6 is pretty beefy. We're not going to cover every single section. There's a lot of sections. There's 9 sections. And we're going to have some days where, like today, we're doing one section. We're going to do one section when we get together on Monday. But next Thursday, it's kind of going to be a summary of logarithms and a summary of the properties, okay? I'm going to do notes on both of those days. That way we can spend the next class time practicing both of those, okay, and having an assignment that does that. Similarly, the following Thursday, I'm going to try to mix these two sections together also, 6-7 and 6-8. That's a special type of logarithm called the common log and another special type called the natural log. And so again, I'm trying to squish 2 lessons somewhat into one. I will scale it down. I will tell you, this is a pretty tricky chapter, okay? So if you are struggling at all, please attend the office hours here, attend the office hours here if you want to. Reach out to me. I'm more than happy to do a one-on-one session if you can't hit up office hours during that time. But a lot of people that just attend office hours end up benefiting from it, okay? Even if you have the work done, hearing it and seeing it one more time kind of solidifies it. Okay, so reach out if you need to, for sure. Just like chapter 5 test, this test here will not be like 25 questions. It's going to be a little bit scaled down so that you can try to get it done in an hour and a half at home. Okay? Alrighty, so we've talked about your test grades. I'm going to try to get them up as soon as I can. We talked a little bit about the calendar that's accessible for you at any point in time, so feel free to reference it, print it out, put it in your own calendar if you need to. Today, we're going to be looking at Khan Academy functions, and not Khan Academy functions, I'm reading below, graphing exponential functions. We're going to watch a really quick little video that kind of lets you see how exponential relationships are developed. Then we're going to talk about exponential growth and decay. I'm going to give you an opportunity to check out Khan Academy and both of those skills. Also, we'll talk about the parent function and practice graphing it. Then I'll have you hop on back on Khan Academy again. So depending on the video, you might choose to actually do this Khan Academy, by pausing the video, or perhaps you decide that you're going to do the Khan Academy later. I want to let you know your homework is to pass both of them with a 75% or higher. Make sure to click submit on the classroom though, okay? So that I know that you've passed them both, and then I will hop on Khan Academy once it's due and once I know that the majority of people have submitted, and I will update your grade online. Okay, so make sure you're getting a 75% or higher on both of these two skills. This one's going to be nice and quick and easy. This one takes a little bit more time and thought. Okay? Alrighty, so let's hop in. Exponential functions is actually kind of a loaded unit right now as far as kind of timeliness in our world, right? I'm sure you folks, if you've followed anything about coronavirus, flattening the curve is the idea of kind of canceling out this exponential trend. So if someone has a virus, or we're going to actually look at it with like a zombie apocalypse today, it's kind of a fun way to look at it. It's increasing very quickly because something can spread very quickly. It actually multiplies versus just adding two every time. So if we think of like one person and they can infect two people, this person can then infect two, and this person can then infect two. So it went from being one person to two people to four people, and then wow, look here, it's going to be eight people. So it's increasing very quickly. The next one is that this eight is going to double, okay, and then it's going to be 16, and then it's just getting bigger and bigger and bigger every time, okay, and that's where this exponential curve comes from. And as people are talking about flattening the curve, they're saying, okay, well, it's already starting to increase quickly. Maybe we can have it increase not so quickly, okay, and it becomes a little different shape versus exponential growth. So, to kind of talk about this in non coronavirus terms, because honestly, I hear a lot about it, I read a lot about it, and I'm ready to not talk about it, let's think about it in terms of like The Walking Dead, right? Like zombie apocalypse style. So, I found this nerdy video. It is nerdy. We're going to watch about 7 minutes of it. And I thought that it's kind of a fun way to talk about the function and the graph and how exponential situations exist without me just lecturing to you about it. So, we'll take a quick look at that.
Hey everyone, Anthony here from Mashup Math. Thank you again for stopping by. I am pumped that you are joining us on this lesson where we get to explore exponential growth in the context of the zombie apocalypse. Hey there everyone, thank you again for stopping by here at Mashup Math on this lesson where we get to explore exponential functions and just how fast a population can grow or how fast a population can decay. Now, as grim as this situation may be, let's see how we can use our math skills to model it and figure out just how long it would take for the entire US to become the undead. Now, before we look at a population as big as the United States, let's start out with a group of just 100 people, and this is before any incident. So our human population would be 100, and our zombie population would be 0. So we can visually model this population of 100 humans using a grid with a length of 10 and a height of 10. So this 10 by 10 grid represents 100 normal human beings. Now at this point, everything is okay until some incident happens and one member of that human population becomes infected. We refer to this as patient 0, and now our human population drops to 99, and our zombie population is 1. And now here comes the chaos. That first infected person will inevitably infect a second person. So now our zombie population has grown to 2 infected individuals, while our human population has dropped to 98. And now we can see how, as this process continues, where the zombie population continues to double, we can see just how quickly the zombie population can grow, while the human population simultaneously shrinks. So now we can see just how quickly an infection can spread, and now we are left with a zombie population of 100 and a human population of 0. They have completely taken over. I got him. Now, if we look at the growth of our zombie population on a graph, as time increased, the zombie population continued to double, and if we express this with a line, it would have to be a curved line and not a straight line, since this is an exponential relationship and not a linear one. Now, on the same graph, let's also show the population of humans as time increases, which decreases by half each time until we are whittled down to zero. Notice that these graphs intersect, and that point of intersection represents the moment when the human population and the zombie population are equal. In other words, we have a 1-to-1 ratio. So for every human, we have a zombie. Now again, these graphs are curves, so they represent exponential functions. In the case of the zombie population, we can call this exponential growth, and in the case of the human population, we can call it exponential decay. So we have one population rapidly increasing over time and another rapidly decreasing over time. So if we want to model growth or decay using an equation, we have to use one in the form y equals a times b raised to the x power. Notice here that our variable is an exponent, which is what makes an exponential equation unique. Now, when we graph an exponential growth equation, our graph is going to be a curve that often resembles a hockey stick, where the initial growth is slow and almost linear, but quickly becomes extremely rapid and exponential. Note that in such equations, the a value always has to be greater than 0. Now, if the value of b is greater than 1, the function will represent growth. However, if the value of b is less than 1 but greater than 0, if it's in between, then the function will represent decay. So now let's go ahead and replace a and b with 1 and 2 respectively, and we can rewrite this function as y equals 2 to the x, just simplified form, and we are going to use this equation to model the growth of our zombie population and see just how long it would take for the entire US population to become infected. So now let's go ahead and graph this exponential function. We are going to label our x-axis as the number of zombie encounters and our y-axis as the zombie population. So now let's go ahead and work on filling out our table. We can start with the value x equals 0, which represents the time before there were any zombie encounters. So in terms of our equation, we have to replace the exponent with 0, and then we can evaluate, and we know that 2 to the 0, or anything raised to the power of 0, just equals 1. So before there are any zombie encounters, we always start with our first infected person, and we should also realize that any exponential equation in this form is going to pass through that point 0, 1, because anything raised to the 0 power is always 1. So these kinds of graphs do not pass through the origin, they always pass through the point 0, 1. And we can reinforce this concept by thinking about that term patient 0 being assigned to the first person who gets infected. Again, because anything to the 0 power is going to be 1. So once that initial zombie has his first encounter with a human, our population grows to 2. After our second encounter, our population grows to 4. After our third encounter, 2 to the 3 power is 8, so our zombie population is 8. So now we can continue this process of inputting x values to find the corresponding y values so that we can see what other points that our graph is going to pass through. And we can continue this process and complete our graph. So from our graph here, we can see that our initial population growth was slow and steady over the first few encounters, but quickly becomes quite rapid, resembling that hockey stick curve that we spoke about earlier. So now that we have run out of room on our graph, we can go back to the table and look at just how quickly the zombie population is growing as the number of encounters increases. So now that we have a better grasp of how populations grow, let's try to...
All right, folks, so that gave you a nice introduction on exponential growth and decay. So growth is where it's kind of increasing like this. Exponential decay is kind of the reflection of that, right? So, right now would be a great time for you to hop on Khan Academy and take a look at this skill. So, exponential growth versus decay. One thing that was not super closely, if you weren't actually taking notes, mentioned in that video is this number right here. Okay, now if you remember, the speaker in that short little video said that if this number is positive but a decimal between 0 and 1, you're going to have a decay. Okay, it's going to be exponential decay. If this number is greater than 1, okay, then you're going to have exponential growth. If you're going to have this as actually just 1, it's going to just be a line, okay? And that's why it's either a decimal smaller than 1 or a number greater. So you're going to hop on Khan Academy. The big takeaway from this is you're going to look at this growth factor. Okay, this is what we're talking about. The growth factor. If it is between 0 and 1, it's going to be representing exponential decay. If it is 1 or greater, it's going to be exponential growth. So you could have problems that look like this, where you choose between A and B and it's a little picture of exponential growth or exponential decay. Or you could have it saying actually just exponential growth or exponential decay as words. So feel free to pause this video. There's a link to the skill in Classroom. I also have sent it to you on Khan Academy, so you can check in either of those locations for it. Otherwise, we're going to just move on. So now let's talk more, now that you understand what an exponential function kind of looks like, right? Whether it's an exponential growth or exponential decay, we're going to look at the parent functions for each of those types. So let me just full screen this thing. An exponential function is going to be a function written in the form of y equals ab to the x. Okay, the fact that you have x in your exponent is your lets you know that it's going to be an exponential function. There's not a number up here. Now you could have an x with a number up here. You could have x plus 2. You could have 2x. That's going to manipulate your graph a little bit. Your b is going to be telling you your growth factor, and we just talked about that, right? If b is going to be greater than 0, not equal to, greater than 0 but less than 1, it is going to be looking at a decay factor, so it's going to be going down. If your b value is greater than 1, then you're going to see some exponential growth. Okay. So something that we haven't seen yet in graphs is an asymptote. Okay, so an asymptote is a line that is not graphed with whatever curve that you're actually doing. It's a line that your graph approaches but never hits. Wow, I spelled approaches very wrong. It should only have one P. Okay, right? Approaches, I don't know. You're going to be kind to me and forgive my spelling right now. So it's going to be a line that your graph approaches but never hits. So for example, you've seen some times of exponential growth, right? A few examples in that video. This line right here is going to get closer and closer and closer and closer to 0, but it's actually never going to hit 0, and it's never going to go below 0. And because it gets closer and closer and closer but never actually hits it, that is an asymptote. And you'll learn this as you start learning more about limits as you continue into pre-calculus. It's not something that you're going to see in geometry, though. Okay, so if that's your next year you're doing geometry, asymptotes won't be part of your conversation, but moving forward, you will see this. Actually, you might see it in the sine curve, potentially. Okay. So this is the parent function for an exponential growth function, right? As we read it left to right, it is increasing. Just like that dude said right here, okay, we have our initial starting point at 0, 1. Our next point is going to be 1 comma b, b being your growth factor, right? Okay, your growth factor. And then here in this one, your third point is going to be to go backwards 1, and then instead of having b, you're not going to subtract b from 1, right? We kind of added it here is what it looks like, but we actually are dividing by b. Remember, an exponential growth function works through multiplication, right? It doubles or it triples or it quadruples every time. So that means if we're going backwards, you would be dividing by it. Okay, here we multiplied to go forward, here we divide to go backwards. A linear function adds to go forwards and subtracts to go backwards. So it makes sense that if we multiply to go forwards, we would divide to go backwards. Okay, and these are just the general points that you would see in a parent function for exponential growth graphs. Okay. So once you have this down, we just like with square roots, you could do all of the other graphs, understanding translations, so shifts up, down, left, right, and multiplication. However, based on some of the feedback that I got from that chapter, it sounds like a lot of people much preferred to just make the XY chart. So we'll talk about being able to make an XY chart to graph our exponential functions. So let's look at actually doing a handful of these exponential graphs. If I look right here, the base for each of my exponents, right, my b value here is going to be, in all of these, it's greater than 1, right? Which means that it is going to be exponential growth. Now this exponential growth could, okay, this exponential growth could have a reflection over the x. It could have a reflection over the y. That happens when we multiply by a negative. It could be shifted up, down, left, right. It could have a different steepness than our parent function. In fact, all of these are going to have a different steepness, okay? Except for this one right here, because this is a base of 2 and a base of 2. So their steepnesses are going to be similar. To graph these, I'm not requiring that you memorize the translations. I will let you know when you add or subtract on the outside, it is a shift up or down, just like you would think. When you add or subtract to the x, you're doing a shift left or right, the opposite of what you would think. And then when you multiply either in the exponent or out front here, okay, you're changing the steepness. And then obviously if you multiply by negatives, that's going to be a reflection. So the translations are very, very similar to what we've done in the past. But what's important for you to be able to do is be able to graph these and understand where the asymptotes are. So if we look back at this graph, right, our asymptote was right on the x-axis. It's that dotted line, right? We can model it as a dotted line right across here, that our line is going to approach, but never hit. So in each of the shifts, if the whole thing is moved up or down, okay, it doesn't matter if it's moved left or right, but if it's shifted up or down, that asymptote is going to be moved also. So for example, see how this has a +1 on the outside? That would be a vertical shift up 1. Now, we don't care about every single point for the graph, but it's very, very important that we understand our asymptote went from y = 0, okay, right on the x-axis, to now being y = 1. It was moved up 1, okay, and again, that's our asymptote. It was shifted up 1. Here, our asymptote, the whole graph is going to be shifted down 5. That means our asymptote that's normally at 0 is going to be shifted down, and it's going to be a horizontal line at y = -5. Okay, that is imperative because when it comes to sketching this graph, you're going to draw that it's approaching this line, but that it never actually hits it. That's going to help you define its shape. So if I were to actually start graphing this one, okay, maybe I'll just go like 1, 2, 1, 2, 1, 2, 1, 2, and make a little XY chart over here. And then I'm going to just graph up my asymptote. Okay, remember it's going to be, it was normally here, dot, 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 dot. The whole thing is shifted up 1, so my new asymptote is going to be at y = 1. So remember, my graph is going to approach this line but never actually hit it. Now, just like with square roots, there are 3 values that are easiest to calculate and then graph. What you want is you want to get your exponent to equal -1, 0, and 1. Because if you look back at this again, -1, 0, and 1 are the 3 points that they're always referencing. So because our exponent is just x, I don't have to say, you know, our current exponent is going to equal -1, our current exponent has to equal 0, and our current exponent has to equal 1. Like, there's no isolating that. Here, I will do x - 2 = -1, x - 2 = 0, and x - 2 = 1, right? Because I want to have those 3 exponents because they're really easy to work with. So I'll start off with, I got x = -1. I'll put a -1 here. So I end up with 2 to the -1 power plus 1. Now, hopefully, if you're remembering back to our exponent chapter, right, a negative exponent means change its location. So this 2 is currently in the numerator. It's going to go down to the denominator. And then this is a 1, so it's going to be 2 to the first. So I end up with not just 2 to the negative 1, I'm going to rewrite it without my negative power. It's going to be 1/2 plus 1, which just equals 1.5. So I'm going to go over to negative 1 and up 1.5 boxes. That's my first point. Now I'm going to do my next one, x equals 0. I'm going to put a 0 right here, so I have 2 to the 0 plus 1. And again, folks, I'm really hoping you remember your exponent properties. Anything to the 0 power, it doesn't cancel out to nothing. It cancels out to be 1. So I end up with 1 plus 1 is 2. So I'm going to go over 0, up 1, 2. I need 3 points minimum to be able to get, because right now that would look like a line, right? To get the shape of the curve, I need to be able to have 3 points, okay? And it's pretty obvious right now. It looks like it's going to be going up just like that. My last x I found is going to be 1. So I'm going to put 2 to the first, which is just 2, plus 1 equals 3. So I'm going to go over 1 up to 3. And if you look, oh yeah, that is increasing pretty steeply, right? And it's going to just keep increasing. Now here's the clincher. This is why we write the asymptote. We don't just willy-nilly draw something here. We're going to draw something that's going to get really close to that asymptote, but never hit it. It's going to be right above it, okay? This is the general shape of this exponential function. 3 points, and our asymptote, and it approaches it, in this case, to the left because it was growth. If it was decay, like we saw in our little video there, it's going to go down, it's going to approach the asymptote in this direction. Okay? Let's take a look at this one. There's no shift up-down here, which would be shown by plussing or minusing, right? Adding or subtracting on the outside. There's none of that, so that means my asymptote is going to be at y equals 0 still. So if I think back to my graph, 1, 2, 1, 2. This is a very messy graph. My asymptote, I'll make it purple like I did on the other one, stays right where it would be in the parent function, right at 0, right on that x-axis. Now this one is going to require a little bit more work, okay? I want this exponent to be equal to negative 1. I want it to be equal to 0, and I want it to be equal to 1. So I'm going to write my x minus 2 to the side 3 times, just like I did with my square root graphs. And I'm going to say, okay, I want this exponent, because this is just the exponent, to equal negative 1. I want it to equal 0, and I want it to equal positive 1. So I'm going to add 2, add 2. When I add 2 to negative 1, I get positive 1. So one of my x values is going to be positive 1. I want it to be 0, so I'm going to add 2, add 2. That means x would have to equal 2. And then I'm going to add 2 here, and that's going to give me x equals 3. These are the 3 x values I'm going to plug in to get out my y's and plot my points. Excuse me. So I'm going to take this one and plug it in. 1 minus 2 is negative 1. I knew that was going to happen. That means this is going to become 1/5. So I currently have negative 1/2 times, remember, multiplying's not bad. We like timesing, but with fractions, 1/5. 1 over 5. So I go across the top, across the bottom, I end up with a negative 1/10. Okay, so I'm going to go over 1 to positive 1 right here, and I'm going to go down 1/10. So I'd have to imagine this is like, 5/10, so 1/10 is right underneath that line. That is very, very close to this asymptote. Now, right now, you might be like, Mrs. White, you said this was going to be exponential growth. Why is that under the line? I want to remind you, when you multiply by a negative, it's going to be a reflection, and this looks like it's going to go from being up here to reflected underneath the x-axis, okay? That negative lets us know it's going to be a reflection. Let's look at our next points and see if we can get the rest of our trend, okay? So next, we'll still have our negative 1/2 in front, times, I'm going to put 2 in here. 2 minus 2 is 0. 5 to the 0 power, or anything to the 0 power, is just 1. So I end up at negative 1/2. So I'm going to go over to 2. I'm going to go down half a box. I'm ready for my next one. Okay. I'm going to change it to green. I got negative 1/2. I'm going to take my 3, I plug it in here. 3 minus 2 is 1. 5 to the first power is just 5. Now I'm going to put that 5 over 1. I multiply across the top. I multiply across the bottom, I'm going to get negative 5 halves. So I'm going to go over 3, and I'm going to go down. I hope you know negative 5 halves is the same thing as 2 and a half. So I'm going to go down. Here's positive 3. I'm going to go down 1, 2, and then half a box. Boom. So you can see, wow, this is really pulling away from the curve here. I'm going to show that. And then to the left, it's going to really start hugging that line. Okay? And there's this graph. We're going to skip over domain and range for now. We will revisit that later. Domain and range. Actually, you know what? We'll do it now. We won't revisit it later. We'll hit it up. That way you've seen it and we're reviewing it anyways. Okay, so it's important for you to see it. So let's come back to this original function here. Our domain looks at our x values. So if we're doing set builder notation, it's all the values of x such that we're going to look for our minimum. There is no minimum. We're going to look for a maximum going out to positive infinity on our x. This continues up, but it also continues out. So if there's no minimum and no maximum, it's going to be all reals. Now, if we were to do this in interval notation, okay, and again, you do not have to do this, but I did introduce it in the previous section. Interval notation has you use parentheses and brackets. A parentheses means it would be an open dot or you're never going to actually reach it. And a square bracket would mean that it would be equals or that I guess you are going to reach it. So because this is all reals, it's going to go all the way from negative infinity to positive infinity. And you actually can never reach infinity, and that's why we use parentheses. Now, if we're looking at range here in set builder, we're going to do all the values of y such that we are going to have some limitations, right? This line can never go below our asymptote. Okay, so this asymptote is kind of the minimum value. You might be like, I don't know, it's not really the minimum, is it? Because it's getting closer and closer and closer to positive 1, but it's never going to equal it. We're still going to use that 1, but because it can never equal it, we're going to show that our y's have to be bigger than 1, but we don't put the equal sign here because it can actually never hit this line. It can actually never equal the 1. To show that in interval notation, and again, this 1 is a minimum, right? But it can never equal it. I would model that with a parentheses, 1, comma, and then there's no max on our y. It continues up forever, positive infinity. If we were to do domain and range on this one, and we're not going to do it on the ones below. We're going to really practice graphing versus practicing domain and range. Our domain here, if we're doing set builder notation, would be all the values of x such that, boom, no minimum. It's going to continue down forever, or out forever as it goes down. No maximum, or no minimum going in this. I'm messed up right now. I'm sorry, folks. There's no minimum on our x, right? Because x-axis goes left and right. Going out to negative infinity on our x here, this continues. Going out to positive infinity on our x, this continues also. It's going down, but it's also coming out. So this one's going to be all reals, which means that in interval notation, it would be from negative infinity to infinity. If we were looking at our range in set builder, we are going to be limited, right? Our asymptote limits us. That asymptote's at 0. So we have y, we have 0. Our graph exists under 0, right? So our y's have to be less than 0, but it can never equal it because it can never equal the asymptote. And in this case, our 0 is the biggest value, right? So if we're thinking of interval notation, there's no minimum, so it continues down to negative infinity. And then our maximum is essentially 0, but it can't equal 0. If it could, we would do that square bracket. Instead, we're going to do a parentheses. So let's go through graphing the next couple ones quickly. And then we'll do 2 of exponential decay. So we're going to first start by drawing our little x and y axis. Here we had a shift down 5, so our asymptote's going to be 1, 2, 3, 4, 5 right here. Now I'm ready to make my table. To get my 3 x values, I'm going to take my exponent, x plus 3, and I'm going to write it 3 times and set them each equal to negative 1, 0, and 1. So I'm going to minus 3, that gives me negative 4. I'm going to minus 3, it gives me negative 3. I'm going to minus 3, that gives me negative 2. I'm going to plug each of these values into here and solve. So -4 plus 3 is -1. 2 to the -1 just means move my 2 underneath. It's 1/2 minus 5. If I'm at positive 1/2 and I go backwards 5 jumps, I'm at -4.5. So I'm going to go over 1, 2, 3, 4 to -4, down 4.5 boxes. Next one, I'm going to plug in a -3 here. So -3 plus 3 is 0. 2 to the 0 power is just 1. And 1 minus 5 is -4. So I'm going to come over -3 down to -4 right there. My last point for this graph, I'm going to plug in -2. -2 plus 3 is 1. 2 to the first power is 2 minus 5, -3. So I'm going to go over to -2 and down to -3. Now, because of the way I made this so sketchy, it looks like it's kind of linear, but we know, okay, here it should be approaching, and then here it's going to be increasing. Okay, and you don't need to actually figure out the intercept. Not a big deal to me. Just these 3 points are perfectly fine. If you want to, pause the video and then come back and look at the answer afterwards. Okay? And this one, my whole graph is shifted down 3. So my asymptote is going to be at y equals -3. So I'm going to go down 1, 2, 3. That's where my asymptote is. I'm going to go to create my table now, my XY chart. I have just x as an exponent, so I'm going to just use -1, 0, and 1, because that's what I would set it equal to. If I plug in -1, I get 1 over 6. So I have 0.1 times 1 over 6 minus 3. Now, because we're dealing with a decimal here, you have 2 choices. You could choose to either make 1/6 the decimal and multiply them, or make 1/10 a fraction and multiply them. It doesn't really matter to me. I'm assuming that most of you are like, Mrs. White, I really like decimals better. And if that's the case, then I will pull up my calculator and we will figure out what 1/6 is. So 1 divided by 6 is 0.16 repeating. 0.1 with the 6 repeating. So we're going to round it up to 0.17. So I'm going to take my 0.17, which is 1/6, and I'm going to 0.17 times it by 0.1. And that gives me 0.017. So I'm at 0.017 minus 3. Again, I just have it on my calculator. I don't care. You guys go for it, okay? It's going to give me -2.983. So -2.983, -1, I'm going to go over to -1. I'm going to go down 1, 2.9. Wow, 8. It's really, 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 really close to this asymptote, like really close to it, okay? Now I'll give my next one a go. So I'm going to have 0 here, 6 to the 0, right? Anything to the 0 power is going to be 1. 1 times 0.1 is 0.1. And 0.1 minus 3 is going to be -2.9. Just 2.9. It's a little bit bigger than this, right? 2.98. This is like 2.90. So I'm going to go over 0, and it's just barely, just a tiny little bit bigger than that. But it is increasing. Now I'm going to look at my last one. I'm going to plug in 1 here. So 6 to the first is 6. 6 times 0.1 is going to be 0.6 minus 3. And that's going to give me -2.4. So I'm going to go to +1. I'm going to go -2. 0.4 is a little bit higher than a half. Woo! So you can see, all right, this is the slow part of this graph right here. But here, wow, it's going to really be approaching right there. Now, eventually this will go way up, right? But we're not there yet. This is where it's slow going in the beginning. Hopefully, after seeing a few more of these, you're feeling good. It's similar. It's a similar strategy to square roots, but a different shaped graph. So let's take a look at our exponential decay parent function. It's the same thing. It has an asymptote at y equals 0 right on the x-axis. So we're going to look for adding or subtracting on the outside to figure out how that shifted. The only big change is something we've already discussed. Our b value, right, our base of our exponent has to be greater than 0 but less than 1, right? It's got to be a decimal in between. So that's going to be the deciding factor that lets us know it's going to start very steeply and end very flatly, hugging that asymptote. We're going to do the exact same strategy for graphing, and we're only going to complete 2 of these. So clearly this is between 0 and 1. Clearly this is between 0 and 1. That's letting me know that it's going to be decay. All right. So is this graph shifted up or down? That you have to know, and the answer to that is no, which means that our asymptote is going to stay at y equals 0. Is this one shifted up or down? Remember, we look for addition, subtraction on the outside. Yes, it is. It is shifted down 3. So my asymptote, instead of being at y equals 0, is going to be at y equals -3. Okay? And that's also going to be the limitations on my range. It's going to be both of those. So we'll make our little graphs real quick. We'll draw in our asymptotes. So this one's going to be at 0. Boom, 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 boom. This one's going to be at -3. 1, 2, 3. And then I'm going to do the exact same stuff that I did before. Okay, so I'm going to find where my exponent is going to equal -1, where my exponent equals 0, and where my exponent equals +1. And in this instance, because this exponent's so simple, it's just going to be -1, 0, and 1. Now, we actually like negatives when it's a fraction, right? Because a negative exponent just means flip it, right? Take this number, move it up here. Take whatever's here, move it down there. So when I have 1/3 to the -1, okay, that means I'd send that here. This 1 goes in the bottom. I'd send this here. This 3 goes in top. So the answer is actually going to be 3. Okay, again, all it means is take whatever you got going on and change its location. So change the location here, change that location there. Remember that 1/3 is in parentheses, so that exponent's applied to both. So I'm going to go to -1. I'm going to go up 1, 2, 3 and put a dot. Now I'm going to plug in 0. 0. So what is anything, whether it's a fraction or a whole number or whatever, what's anything to the 0 power? It's just 1. There's nothing added to it. There's nothing multiplied to it. It's just 1. So I'm going to go over 0, up 1. Now my last one is 1. So anything to the first power is just itself, right? So here's where a fraction starts tying in. At 1, I'm going to go up only 1/3 of a box. So, oh, there's the shape that I was looking for. It decreases very quickly, and then it gets close to that asymptote. Okay. Again, my domain here, we're just going to talk about these. No maximum on my x, no minimum, all reals. My range is that my graph has to exist above my asymptote. So my y's have to be greater than 0, can't equal it, greater than 0. If I were to do that in interval notation, right, it would be an open, well, not open, I guess it would be a parentheses, 0, comma, positive infinity. Okay, if I was to do domain and range, I would put all reals, or if I was doing that in interval notation, I would say from -infinity to infinity, both with parentheses. This one's a little bit more complicated, right? I graph my asymptote first. We already did that. To get my x and y values, I have to take my exponent. I want my exponent to equal -1. I want my exponent to equal 0. And I want my exponent to equal 1. Okay, so I need to subtract this time. I'm going to -2 and get -3. I'm going to -2 and get -2. I'm going to -2 and get -1. Now I'm just going to plug and play. Okay, take this -3 here. -3 plus 2 is -1. A negative power means flip this around, right? I'm going to have 2 times, not 1/4 anymore. It's going to be 4 minus 3. So 2 times 4 is 12. 12 minus 3 is 9. Okay, that's going to be big. So at -3, 1, 2, 3, I'm up. Ooh, this is not going to be very consistent. 1, 2, 3, 4, 5, 6, 7, 8, 9. Woo, way over here. Now I'm ready to do my next point. I'm going to plug in -2. -2 plus 2 is 0. Anything to the 0 power is 1. So I'm left with 2 times 1, which is 2, minus 3, which is -1. So at -2, it's way down here already. Look at how fast that went. Okay, that was very, 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 very fast. Now let's do our last point here. We'll plug in -1. -1 plus 2 is 1. That means my 1/4 stays the same, anything to the first. So I have 2 times 1/4, which is going to be 2/4, or just 1/2. 1 half minus 3 is negative 2.5. So at negative 1, I'm going to go down 1, 2.5. Again, my scale's a little wonky here, right? So this isn't going to look like a nice smooth curve like it should, but you can see here, whoa, it's going to start hitting that, okay? If these were a little bit better, then this would have come down like this a little bit more clearly, okay? But there's our exponential decay, right? Quick at first, slows down towards the end. If we were to do domain and range here, it'd be all reals for our domain, and then our range would be anything greater than negative 3. Again, because negative 3 is a minimum, it would be a parentheses if you were doing interval notation. Okay, and it would be listed first. So it would be parentheses negative 3, comma, positive infinity for the range. So now that we've graphed these, hopefully this strategy feels familiar and you'll be good to go. Your homework is to graph exponential growth and decay on Khan Academy. Now, Khan Academy is only going to ask you to do 2 points. That's fine with me. Obviously, it's got to be fine with me because I'm assigning this Khan Academy to you, okay? However, know that when you see it on an assessment, you are going to be asked to do 3. Okay, we just did 3 together. So I want you to use that same strategy, but you only have to graph 2. Okay, and remember, if you're taking your time on these, you only have to do 4 or 5 problems to get that 75 or better. Alrighty? If you're having any issues, like always, please, please, please come see me during office hours. You're welcome to turn this off right now, but I am going to solve one of these on Khan Academy just so you can kind of see how to move those dots around. If not, I will talk to you folks later. So to go about graphing this one, folks, again, you have a very simple x value. So we could just plug in, for example, we could plug in negative 1 if we wanted to, or 0 or positive 1. I'd probably plug in 0 and positive 1 since we only need to do 2 points. So if I put a 0 here, anything to the 0 power, okay, is going to be 1. 4 times 1 is 4. So my coordinate pair is technically what I plugged in for my exponent, which was 0. And then remember when I plugged in 0, I ended up with 4. So I'm going to take this first point, I'm going to move it up to 4. Then my next point that I'm going to do, I'm going to plug in 1 here. And then I'm going to know that anything to the first power means it stays the same. So I'm going to do 4 over 1 times 3 halves, which gives me 12 over 2, which is 6. I know I just did that really quick, right? 12 over 2 is 6. I plugged in 1 for my x value. So I'm going to go over 1. Be careful of scale here, right? Over 1 is here, up 6. And it's going to make the rest of the curve for you. If you had a plus 2 here, okay, which we don't, you would see how I can move this asymptote. You would move the asymptote. Don't just do 2 points, okay? You have to move the asymptote also or it's going to mark it wrong. I did not shift it because there's nothing being added or subtracted here, but maybe you should move that asymptote as your first step. So I'm going to boom, boom, check-a-rooney. What? Give it another shot. Oh, it's because I moved it up. Oh, man. There we go. See, I should not have shifted it up because that didn't exist, but for whatever reason, I did. So let's look at our next one. Again, they did not shift it up or down, so my line is going to stay here. I do want to point out that this fraction, this growth factor right now is less than 1. So this point is going to need to be dragged over here at some point, okay? So you can do that to make sure that you're representing that exponential decay. I don't want to do too many of these because I want you to be able to be, you're only going to have to do 4, right? I want you to be practicing independently, and I don't want you to get the same exact examples that I do. So remember, shift this up or down if we need to. Okay, and then find your 2 points and it will do the rest of the curve for you. All right, folks, that's it for me. I will catch y'all on the flippity flop. Have a great afternoon, great day, great evening, great morning, depending on whenever you're watching this. Bye.